Hello Physics 20s, it's Mr. Hofstad here with Unit 4, Lesson 4. It's our first non-review from Science 10 lesson in this unit. So let's give it a go. If there are any questions, of course, please email me and let me know. This one is a little bit different, a little bit harder conceptually than our first two types of energy, but hopefully you've all seen springs. I usually use a slinky for a whole bunch of these. I'll see if I can find my slinky anywhere lying around. So we're looking at springs today, or elastic force. I can't find my slinky. Oh well, we'll have to just imagine. So, springs and elastics kind of work similar to gravity in that they store energy, right? As we lift something up off of the ground, we're transferring gravitational potential energy. It's storing that energy, and it'll convert it to work once you let the object go. Because gravity will apply a force over a distance until it returns to the ground. So similar to that, we have springs that we can compress or we can stretch. And when we compress it, right, we're storing energy in those compressed coils of our spring or our elastic. And once we release it, that spring is going to apply a force some distance until it returns to its natural, which we call rest length. And similarly with extension, as we pull a spring or a slinky or whatever we're looking at, even a rubber band, as we stretch it apart, right, we're storing energy in those stretched coils here, and once we release it, it's going to apply a force now in the opposite direction back until it's reached its rest length once again. So it'll apply that spring force some distance doing work. So our general equation here, we have the force of the spring, the elastic force or the spring force, however you want to look at it, is equal to negative K, where K is our spring constant, times the x, which is our displacement. Alright, so there's our general formula for any spring force. And this, of course, needs some assumptions, as all things in physics tend to need. So we can only use this for what we call an ideal spring. So that's a spring that is perfect in its stretchiness and its stiffness, and it won't lose its shape as we stretch it. So x is the displacement from rest length in meters. That's super important, and that's going to be an easy one to get confused on and to forget. So that's what we're looking at right here with our x and this arrow. So that's the displacement from rest length. So we're always going to need to calculate or identify how long the spring is at rest when there's no force, no weight, nothing applied to it. And then the x value will be how far we are away from that as we're compressed or stretched. So it's a displacement from that natural, normal spring rest length. And K will be different for every spring. It's the spring constant. It's how stiff the spring is. Right? K represents the stiffness of the spring. So we need to take note of this negative sign. Force of spring is negative Kx, negative spring constant times displacement from rest. It'll always be in the opposite direction to displacement, right? And you can see that from this diagram here. If our displacement is to the left, if we're compressing our spring, that means our spring force is going to be to the right. It's going to be returning it to where it came from. That's because the spring force is what we call a restoring force. Right? So you could just write a little note of that if it'll let me. No text box. Okay. You can call this guy a restoring force. That's another physics word you'll hear come up with this. So the higher, going back to the K, right? We know that the spring force is always opposite to X. K is the stiffness. So higher K is stiffer, which means we need more force to stretch or compress the spring. So if you have two different springs, one has a K constant of 100, one has one of 4,000 newtons per meter, it's going to be really easy to move the 100 newton meter versus the 4,000, right? That's what we refer to as the stiffness of the spring, how much force it requires, right? That's where the units come into play. Newtons are our unit for force, and they're per meter. So how many newtons it takes to stretch or compress our spring 1 meter. Right, 4,000 newtons to stretch or compress 1 meter of our rest length, coming from our units, as well as this formula, right? K is equal to force of spring divided by displacement X, newtons over meters. Okay, so that's our equation for the force of a spring. We refer to that as Hooke's law because I don't remember if it was Robert Hooke. There's a Robert Hooke who is often referred to in biology. This might be the same guy who came up with the spring. Might be a different guy, might be a relative. But there's our spring force. Here's our potential spring energy, elastic potential energy. So we use this lowercase es to kind of tell us what we're working with there. I don't want that all. Okay, es is half of kx squared. So elastic potential energy, right? Almost like spring potential energy, that's where we use the s. Or you could think of it as the stretching energy due to stretching or compressing an elastic material. So this doesn't have to be a spring, right? Even though we're using ES, think about it as anything that could be stretched or compressed. Rubber bands, springs, shocks on a car, all of those have some elastic potential energy. And what does this look very similar to? What formula? It looks very similar to our kinetic energy. Half of mv squared for kinetic energy, half of kx squared for elastic potential energy, right? And they're both units of energy or joules, right? And we're using the same k and x as we did for our force. So k is how much we've stretched or compressed from rest, and k is our stiffness, our spring constant, right? And if we take a look at the units, we get newtons per meter from this one, and meters squared. So we get Newton times meter, and that is a joule. A joule is also a Newton meter, right? And if you break Newton into its units, kilogram meters per second squared, we get kilogram meter squared per second squared, which is a joule. All right, ever so important to take a look at our units. Okay, let's give this example a shot. We have a spring with some rest length that we have to measure. It's not given to us. We're going to call it 37 centimeters at rest. And once we have it attached to this mass, we're going to say we've stretched an additional 12 centimeters. Those aren't given in the question, but that's what I'm working with here. So the total length of the spring with the mass attached would be 49 centimeters. And our mass, of course, is 500 grams or half a kilogram. Okay, let's take a look at this together. So our rest length is 37, and our stretch length is 49, right? That's usually what you would be given in a question, right? Stretch length is 49, rest length is 37. So our x is equal to our stretch minus rest, which in this case is equal to 12 centimeters. Okay, so you're usually going to have to calculate this x value. All right, so we've got our measurements down. We'll say that our reference is up is positive, down is negative. And if the spring and the system is at rest, right, we're no longer accelerating up or down, we're going to use our principle of physics 0, Newton's first law. The net force is 0. So our net force, if we look at this mass, we have a force of the spring pulling it upwards, right? We've stretched the spring 12 centimeters down, and we know that the spring force is negative k times x, so it's going to be in the opposite direction of our stretch distance, or our x. So our x is down. Our force of the spring, or our elastic force, is up, right? And of course, force of gravity is pulling this down to the ground. So our two forces acting on this mass, right, the two external forces on this system of the mass, are force of gravity and force of spring, or elastic potential. So we have the force of spring up and force of gravity down, and they need to equate to 0 newtons. So our force of spring is equal to our force of gravity. The question wants us to determine the elastic energy, so we're going to break open this spring force into its components, negative spring constant k and x is equal to our mass and our gravity. All right, force of spring is equal to negative kx, force of gravity is equal to mass times gravity. So we know x, we know m, we know g. In order to solve for our elastic potential energy, we need half of kx squared. We already know x, we're looking for k. So we're going to solve this for k. K is equal to negative, I'm just going to bring the negative to the other side, negative mass times gravity divided by x. But in this case, x would be down, which is negative, so we'll cancel those out, you'll see. Negative 0.5 kilograms. Gravity is 9.81. And we're dividing it by negative 0.12 meters. 12 centimeters we need to convert to meters. And this comes out as, negatives will cancel, we have 40.875, and our units, kilograms, meters per second squared, right? Kilogram, meter per second squared, turns into a Newton, right? Mass times acceleration becomes newtons, right? And these are the fundamental units of a Newton. So we have newtons per meter, which is what we needed for our k constant. Good. Now we're ready to throw it all back into our energy equation for our elastic potential energy. We have half of 40.875 and our x value squared. Since it's squared, you don't have to worry about positive or negative. Also, energy is scalar, meaning direction, positive, negative, doesn't matter. So 0.12 meters squared. Right, and this is a Newton per meter if we're looking at the units. So the units, even before we do any calculations, will be newtons per meter times meter squared, or Newton meters, which we know is a joule. And this comes out as 0.29 Newton meter, or 0.29 joules. We'll usually stick with joules. That's our standard unit for these. All right, there's our first example. Let's take a look at some energy conversions. So here we're kind of combining these last three lessons with kinetic potential and now gravitational potential, and now spring potential. We've got two types of potential going on. So we need to remember that when work is done on an object, energy needs to change because work is equal to change in energy. So two ways energy can change. They can either transform. This is when it changes. So the key word here, energy changes from one form to another. Right, so that's kind of within the same object, right? When we're dropping a ball from some height, we'll transform, gravitational potential energy into kinetic energy. It's still saying within the same object though. So that's always happening within one object. Transfer is between two different objects. So we're getting energy going from one object to another. For example, when a bat hits a baseball, we're transferring kinetic energy from one object to the other. So transfer requires obviously the transfer of energy, which by definition needs to go from one object to the other. Transformation, right? Think about Transformers, robots in disguise. Optimus Prime, he's one object, but he's changing from one form to another. Whereas transfer, I don't know, think about an e-transfer. You need to give your money or your energy to another person or another object. Maybe that will help you to remember the differences between these. Transformers, Optimus Prime, and e-transfers. So when we're describing energy conversions, we need to include changes in energy. So the types, right, that would be our gravitational potential to our kinetic. So from what form of energy to what form of energy. We also need to talk about the objects, right? That would be from bat to baseball. Or, right, if it's just staying within the same object, we don't have to worry about that quite as much. Okay, let's look at this cool shooting inclined spring for an example. So starting off with this box or object at rest. So it's got this spring compressed, obviously. We kind of looked at this with our projectile launcher. It's similar to that, where we shot our little orange balls and measured the distance that they launched back when we were actually allowed to be in school. Sad reminder of not being able to see you guys for so long, but this is essentially what's happening, right? It's storing this spring energy. We're releasing it from rest, and this compression is getting shot up the incline. It's going to continue upward a little bit, and then it's going to arc downward, right? This kind of 2D projectile motion into the water below. So assuming no air resistance while it's in the air and no friction while it's on the ramp. Also probably assuming this is an ideal spring, so we can use, well, I guess we're not doing any math, so that's not crazy important. But no friction in the spring either. So we want to identify energy conversions, right, which can be broken up into transformation or transfer. So the first stage, release of the spring. So I think we can even break that up into, no, we'll just look at that as one. It's too bad that my text isn't working. Oh. I'm going to try to get it working. Sure, let's try it like this. Little sticky notes it looks like. Can I make it white? Yes. Maybe not. Okay, so once it's been released from rest position, the spring tension from compression is going to decrease, right, as it's been compressed. Once it's released, we're going to get that force of the spring, right, pushing it out, and we're decreasing the compression. Here we're looking at energy though, so as that spring tension decreases, the energy stored in the spring will be decreased. But as that happens, the energy is being transferred to the box as the object speeds up and gains height because it's going up the incline. So that would look like our spring energy being converted here. Let's just do it on our whiteboard. So we have a starting spring energy, ES, or energy stored as elastic potential energy. That's in our spring. Right, this is when it's compressed. And it's going to be converted to our kinetic energy and potential gravitational energy in our object, in our box. Right, and that's as it moves up, right? So the energy of motion is the kinetic, and the energy of the height gained is our, wow, I can't draw a slanted box right now. Right, as it increases height, we're gaining potential gravitational energy. So we identified this transfer from the spring to the object, as well as this transformation, right? I guess it's more of a transfer because we're going from one object to the other. But we're also getting a transformation. So yeah, the transfer part is from our spring to our object. And the transformation part is the change in form of energy. So we're changing the form even within the object, but more importantly, we're transferring from the spring to the object. Okay. Next one. We're going, this is unfortunate. So once it's in the air now, we're going up to the maximum height. So we're going to be gaining height essentially. What do we remember about our maximum height though? for an object in this 2D projectile motion to reach its max height, what is its speed going to be, at least in the y direction? It's going to be 0. So we're losing what type of energy? If we're losing speed, we're losing kinetic energy. So what that really means, let's get my little sticky note. We're going to lose speed, which is going to be our kinetic energy, but it gains height, gravitational potential. Okay, so if we look at that again on the whiteboard, which I just have to erase, right, we're going in the air upwards to reach this max height, right? So we're gaining height, but our speed in the y direction is 0. So we're having this Ek in our object, kinetic energy in the object is turning into our gravitational potential energy in the object. So are we having any transfer of energy here? No, transfer requires it to go from one object to the other. We're looking at the same object, so all we have is a transformation. It's transformation of Ek to potential gravitational energy, right? Because it's within the same object. So there's no transfer. Okay, so we're losing kinetic energy as we're slowing down in that y direction. If we remember from Unit 2, our horizontal speed is constant throughout that motion. But in the y direction, right, we're going to be losing our speed in that vertical direction, right? And that loss in speed translates to a loss in kinetic energy because we're looking at half of mass times speed squared. So that loss in speed is converted to a gain in height, right? Kinetic energy to potential gravitational energy. And then the object is going to stop traveling up, right? It's reached its max height, and it's going to continue down into the water. So we're going to now have the mass losing height and gaining speed. And again, that gain in speed is only from the vertical direction. Because our horizontal speed is constant. So we're losing height, but we're gaining speed down, right? Energy scalar, doesn't matter what direction that speed is in, right? It'll still be a gain in kinetic energy. So we have our box now coming down, right? And we're gaining, well, we're increasing our speed in the y direction and we're losing height. So we're having our gravitational potential energy that we just gained in our object being transferred to kinetic energy, also in object. So once again, just like our last point, we don't have a transfer, we only have a transformation. And last but not least, when it hits the water, this is the most fun one. We got to think about a lot of different things. It's going to be losing its speed, right? It'll lose some height. It might bob below the water. It's also going to create waves and noise. So we have a bunch of different things happening here. We've got different energy forms that we don't look at extensively, but we should just be aware of. So we now hit the water, we've splashed, we have waves coming off the box, splashes, drips, and noise. So we're converting all of this kinetic and maybe some potential gravitational if it bobs below the surface for a little bit. Right, we might get a negative potential energy if we have a reference height of 0 here and we're dropping below it. We get a negative height, we get negative potential energy. And that's going to be converted into wave energy. We'll look at waves more in Unit 6, but waves actually do carry energy. So we're going to have these, if the block or the box is dropped here, we're going to have these ripples going outwards, right? You've seen that if you ever throw a rock in a pond or something. That's actually transferring energy through the water in these waves. So we're going to have wave energy. We're going to have some kinetic energy in the water. We're going to have sound energy in both the air and water. Right, you'll still hear it if you're underwater. And a little bit of heat. Mostly in the water. Okay, so we don't only have our 3 types of energy here. We're working with wave energy, Unit 6 stuff, and we're working with sound, also Unit 6, and heat, which is usually just waste energy that we kind of ignore. So yeah, that's going from the mass, or from the object, sorry. So we got kinetic and gravitational potential in the object, and it's being transferred to the air and water, and it's also being transformed. So since it's energy going between 2 objects, or 3 objects if you count air and water, we have a transfer, and we also have transformed because we're changing type from kinetic and potential gravitational to wave, more kinetic, sound, and heat. So that's all we got for this lesson. Good luck with the homework. Let me know if you have any questions. This one, kind of a double whammy. We're throwing a new type of energy that we've never looked at, elastic potential energy, and this kind of new idea of energy transformation and transfer. So take your time with this homework. Make sure that you got a good foundation for this, because this is important and it's going to come up a lot for the rest of the unit. Alright, good luck everybody. We will have another video up for you shortly. See ya.